Welcome to This Explainer. Today, we're going to completely unravel a really fascinating procedural mystery. We are essentially stepping into the shoes of a chemical detective to answer a question that has honestly baffled novice chemists and thrilled experts for decades. How exactly do you identify an unknown chemical substance when your eyes alone give you absolutely zero clues? Well, today, we're going to see how scientists solve this exact mystery using a powerful, really elegant technique known as thin layer chromatography.
So, imagine you're standing in a laboratory. On the bench right in front of you is a tiny vial containing a clear liquid, or, maybe a white powder dissolved into a solution. It looks exactly like water. Actually, it looks exactly like 1,000 other chemicals. You can't safely smell it, you definitely cannot taste it, and just looking at it tells you absolutely nothing. You have zero clues to go on. So, how do we figure out its true identity? How do we literally separate and identify the invisible?
Okay, let's dive into this. Our primary investigative tool for today's chemical whodunit is thin layer chromatography, which is often just called TLC. At its core, it's a brilliant technique used to separate non-volatile liquids, basically liquids that just don't easily evaporate at room temperature. It works by measuring how these substances move through a solvent across a specially coated thin layer. It's essentially a microscopic racetrack where chemicals get separated based on their unique molecular personalities, specifically their polarity.
Here's our quick roadmap for today. We're going to cover 1. The science of separation, 2. Preparing the TLC plate, 3. The polarity race, 4. Visualizing the results, and 5. Calculating the RF value.
Let's kick things off with Section 1, the science of separation, setting the stage.
Right, so all forms of chromatography basically rely on a dynamic relationship between two critical components, the mobile phase and the stationary phase. You can kind of think of the stationary phase as the terrain and the mobile phase as a river flowing right over it. In our specific TLC setup, the mobile phase is our liquid solvent. We're using a mixture of 95% ethyl acetate and 5% acetic acid here. The stationary phase, on the other hand, is our TLC plate, which is just a piece of glass or plastic coated in a very, very thin, delicate layer of an adsorbent material like silica gel. As the solvent travels up the plate, it just carries our chemical mixture along with it, separating the components out as they interact differently with that silica.
Moving right along to Section 2, preparing the TLC plate, also known as the suspects.
Every good mystery needs suspects, right? We're testing 4 distinct samples today. Caffeine, which is our first known standard, aspirin, our second known standard, a mixture of both just so we can see how they behave when combined, and finally, sample U, our mysterious unknown. Our entire goal today is to figure out for sure if sample U is caffeine, aspirin, or, maybe a mixture of the two.
So let's see how this actually works in the physical lab. It's a very delicate process. First, we use a pencil and never a pen because pen ink will just travel right up with our solvent to draw a gentle line about 1 centimeter from the bottom of the plate. We draw it really gently because that silica gel layer is incredibly fragile. If you scratch it, you literally ruin the track. Next, we mark 4 evenly spaced dots on the line for our samples. Finally, we use these tiny glass microcapillary tubes to apply a super small drop of each sample onto its designated dot. You just tap it gently against the plate a few times. And crucially, we absolutely must use a brand new tube for every single sample to prevent cross-contamination. We want our results to be completely unambiguous.
Okay, before we proceed, I really have to emphasize the highest stakes rule in the entire lab. The solvent level in your chamber absolutely must sit below the pencil line you just drew. When we place this plate into the glass chamber with our 5 milliliters of solvent, if the liquid level is too high and touches those sample dots directly, the chemicals will instantly wash off the plate and dissolve straight into the solvent pool. The experiment is instantly ruined, and yeah, you have to start the whole shebang all over again.
Now that our plate is safely prepared, we enter Section 3, the polarity race. Ready, set, go!
Now, what's really interesting about this is the invisible microscopic battle happening right before our eyes. As the solvent creeps up the plate via capillary action, it drags our samples right along with it. But the silica gel on the plate is heavily covered in hydroxyl groups, which makes it highly polar. It acts like a giant sticky obstacle course. Polar substances form electrostatic interactions with the silica, getting stuck and moving very, very slowly up the plate. Nonpolar substances, however, they don't care about the sticky silica at all. They just ride the solvent wave and travel much faster and farther up the plate. This precise difference in speed is exactly how the chemicals separate.
While this race is happening, you really cannot look away.
You have to cap the chamber to keep the atmosphere fully saturated with solvent vapor. Then, you actively monitor the solvent traveling up the plate. You've got to remove the plate right before the solvent front hits the very top edge. And here is a totally critical maneuver. The absolute second you take the plate out, you must use your pencil to quickly trace the exact line where the solvent stopped. Why? Well, because the solvent will evaporate in seconds. And if you don't mark that invisible line right then and there, you won't know how far the solvent traveled, which means you can't do your math later.
All right, the race is over, the plate is completely dry, and that brings us to Section 4, visualizing the results, the big reveal.
So, you're holding your dried TLC plate, and you look at it, and, well, it looks entirely blank. Aside from your pencil lines, you literally can't see a thing. This is a massive problem because most organic compounds are completely invisible to the naked eye. But don't worry, chemists have a spectacular solution, and it is honestly my absolute favorite part of the process. We are going to use a UV lamp to reveal the hidden chemistry.
When we place our blank plate under a specialized UV lamp, something truly magical happens. Compounds that contain systems of pi electrons will absorb the UV light and visibly glow. Or they'll create these really dark shadows against the fluorescent background of the plate. Suddenly, our invisible chemical finish line just lights up. While looking under the UV light, we take our pencil and carefully circle the final resting spots of our samples. Oh, and a quick safety reminder here. UV light can really damage your eyes, so always wear protective eyewear when you're operating these lamps.
And this brilliantly illustrates the solution to our mystery. Just look at those final positions. Sample A, the caffeine, traveled a very short distance, which tells us it's highly polar and got stuck on the silica. Sample B, the aspirin, traveled much farther, meaning it's way less polar. Our mixture lane clearly separated into two distinct spots, confirming both substances are present there. But the big reveal? Sample U, our unknown, traveled the exact same distance as sample B. We did it! We have successfully identified our unknown liquid. It is undeniably aspirin.
Visual confirmation is incredibly satisfying, but in science, we always need to back up our eyes with cold, hard math. Let's move to Section 5, calculating the RF value.
To properly quantify our results, we calculate something called the retention fraction, or the RF value, for every single spot on our plate. The equation is beautifully simple, really. You just take the distance traveled by the sample, and you divide it by the total distance traveled by the solvent front. That's it.
So, the crucial point is that your resulting RF value will absolutely always be a decimal less than 1. Think about the physical reality of our experiment for a second. A chemical sample can never, ever travel farther or faster than the solvent wave that's actually carrying it. Therefore, the numerator is always going to be smaller than the denominator. Honestly, if you ever calculate an RF value of 1.2, you've definitely done your math upside down.
Let's quickly walk through the physical procedure with just a standard ruler. Step 1, you measure from the start line to the middle of the sample spot. Step 2, you measure from the start line to the solvent line. Step 3, you divide the two. And Step 4, you compare this numerical fingerprint to known tabulated data. Once you have that RF value, you can confidently verify your chemical in that specific solvent against massive charts of known chemical data.
So why does mastering this little glass plate actually matter to us? Well, in major laboratories all around the world, TLC is an absolutely indispensable rapid qualitative tool. Chemists use it constantly to confirm if they've successfully created a desired product after a really complex reaction. They use it to monitor reactions in real time, literally taking tiny samples every hour to see if the starting materials have disappeared yet. And, vitally, they use these tiny plates to rapidly test out dozens of different solvent mixtures just to find the perfect one for separating their specific chemicals. Which leaves us with a truly fascinating question to ponder. TLC is amazing for screening microscopic, qualitative amounts of a substance. But what if a pharmaceutical company needs to physically separate, isolate, and collect massive, industrial-sized buckets of these chemicals? How do we scale